All right, the intersection of set A and set B, written A intersection B, is a set of all elements that are common to set A and set B. In other words, in order for you to make it into the intersection of set A and set B, you would have to belong to set A and also set B. The union of set A and set B, written A union B, is a set of elements that belong to set A or set B or both. In other words, if you belong to the union of set A and set B, then you are either in A or you're in B, or you could even belong to both. Here's a picture to go with that, with these definitions. If this is set A here, and then this is set B here, A intersection B, basically all of the elements that are in set A and set B would be this shaded region. This shaded region here represents A intersection B. Now let me show you a picture of what A union B would look like. Again, we have set A over here, we have set B here, and any element that belongs to A or belongs to B makes it into the union. So anything in A, anything in B makes it into the union. Even elements that belong to both make it into the union. So then all of this represents A union B. Basically, the only elements that do not make it into the union of set A and set B are those elements that are in neither A or B. So for example, if there was an element out here, like out here somewhere, this element would not belong to the union because it's in neither A nor B. All right, example 1. Let's set A be -5, -3, -1, 1, 3, 5. So A is a set of all these numbers or elements. Set B contains 0, 1, 2, 3. The first thing I want you to consider finding is A intersection B. So find A intersection B. Now, A intersection B by definition is a set. So I'm going to start by writing a set. I got to use braces. And the elements that are in the intersection are those elements that belong to A and belong to B. Let's see. Does -5 make it into the intersection? No, because -5 is in set A, but it's not in B. Does -3 make it into the intersection? No, because -3 is in A, but it's not an element in B. Neither does -1. But the number or the element 1 makes it into the intersection because it's in set A and it's in set B. So I'm going to add the number 1 here. The only other element that's in both set A and set B is 3. So this is the intersection of those two sets. The next thing I would like for you to consider is A union B. Find that set. Remember that any element that is in set A will make it into the union. Any element that's in set B will make it into the union. Any element that's in both set A and set B also makes it into the union. So basically, all of these elements that are in A make it into the union. So I'll just copy and paste basically all of the elements in set A into the union. I'll go over here now to elements in set B, copy and paste those into the union. So 0 makes it in, 1 makes it in, but wait a minute. I already have 1 listed, so I do not write it again. 2 makes it in, 3 makes it in, but wait a minute, 3 is already listed, so I don't write it again. So then this is the union. I don't bother writing these numbers in order from least to greatest because order doesn't matter in set notation. Now that you and I understand what intersection means and the union of two sets mean, let's now start solving compound inequalities. All right, everybody, this is a compound inequality because it's two different inequalities joined together by this conjunction word that is and. Now, this is what is really important. You have to know that whenever they use the word and to join these two inequalities, the word and implies intersection. That's the symbol for intersection. You're going to keep that in mind when we get to the very end. Okay, guys, the way we solve a compound inequality is we solve each inequality separately. So solve this one and then solve this one. So let's take the first one here. 2x plus 3 is greater than or equal to 5, and let's solve it. All right, so I'll write it over here. 2x plus 3 greater than or equal to 5. The first thing I'll do is I'll subtract 3 from both sides. Okay? Remember, we want to keep the variable on the left side if we can. And now I have 2x is greater than or equal to 2. The next thing I'll do is I will divide both sides by 2. And then I have my final statement, which is x is greater than or equal to 1. Keep that in mind. Now let's go to the other one. X over 3 minus 2 strictly less than 1. First thing I'll do here is add 2 to both sides. That will leave me with x over 3 is strictly less than 3. What I'll do next, in order to isolate the variable, is multiply both sides by 3. Multiplying the left-hand side by 3 isolates your x variable, and you have x is less than 9. All right, there it is, everybody. Now, this is very important that you understand that they are asking you to find all the values of x that satisfy this compound inequality. That means you have to find all the value of x that satisfy this inequality and this one. It's not good enough to just satisfy one of these inequalities. You must satisfy both of them. That's what the word and implies. So all of the numbers that satisfy x is greater than or equal to 1 and less than 9 make it into the intersection. So here is the graph of our solution set. Let me show you a picture. Okay. So here is the number 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's the number 9. So in order to make it into the intersection, you have to be a number that is both greater than or equal to 1 and less than 9. The numbers that are greater than or equal to 1 are in this direction, but the numbers that are strictly less than 9 are in this direction. So basically all of the numbers between 1 and 9 are those numbers that are greater than or equal to 1 and at the same time less than 9. I'm going to put a bracket on 1 because that inequality symbol is non-strict. I'll put a parenthesis on 9 because this inequality is strict. So basically, 1 makes it into the intersection, but 9 is not included in the intersection. The last thing I'll do is provide the solution set in interval notation. Remember, interval notation means that you want to read your graph from left to right. So as I read my graph left to right, I read a bracket at 1 all the way to a parenthesis at 9. When you solve these compound inequalities, which we're done now, there's 3 parts to it. You showing all the algebra, right? And then you finding the graph of the solution set and then writing the solution set in interval notation. All right, the next compound inequality says 3x plus 4 is less than or equal to 2x plus 6. And, there's the word and again. So I'm going to remind myself that this means intersection. 5x minus 2 is strictly greater than 7x plus 2. All right, let's take each one of these inequalities separately. Here we go. 3x plus 4 less than or equal to 2x plus 6. What I'll do first is, remember, I want to keep my variable on the left side. So I am going to subtract 2x from both sides because I want to keep my variable on the left. So what that will do for me now is give me just 1x plus 4 is less than or equal to 6. Next, I will subtract 4 from both sides and get my final statement that says x is less than or equal to 2. All right, let's go for the next inequality. Okay. The next inequality says 5x minus 2 is strictly greater than 7x plus 2. Again, I want to keep my variable on the left, so I'm going to subtract 7x from both sides. That leaves me with negative 2x minus 2 is strictly greater than 2. I'll then add 2 to the other side, to the right side. Well, actually, I'm adding 2 to both sides, right? So I have negative 2x is strictly greater than 4. What I'll do next is divide both sides by negative 2. Remember, whenever you divide an inequality by a negative value, you have to flip the inequality. That's easy to forget, so be careful. All right, everybody, we did it. We solved each inequality separately. Now we have to interpret the results. Any value of x that is both less than or equal to 2 and strictly less than negative 2 make it into the intersection. It might be better for us to see a picture of what's going on. So let's see if we can graph the final solution set. All right, so I'm going to say this is a negative 2 here, negative 1, 0, 1, 2 there. This one here says any number that is less than or equal to 2. Let me show you that now. Less than or equal to 2 means that way, less than or equal to 2. Whereas this one says numbers have to be less than negative 2. So actually, let me do it like this. Maybe this will be better for our vision, okay? Let me go back if you guys don't mind. Less than or equal to positive 2. Let me do it this way. Let me do it right above, like that. And now, strictly less than negative 2 would look like this. Strictly less than negative 2 look like this. Now, this is not my final graph. This is just me kind of brainstorming here, guys. Remember that intersection of these two sets mean you're looking for all of the numbers that are in both sets. The numbers that are in both sets will be this overlapped area. These numbers do not make it into the intersection because they're not in both sets. They're only in the green set. They're not in the yellow. So the intersection or the overlapped area starts at negative 2 and then goes that way forever to the left. So then a final picture can be this. If this is negative 2, then a final picture can look like this. From negative 2 that way. Now, a question I have for you is, do I or should I put a bracket at negative 2 or should I put a parenthesis at negative 2? Well, if you put a bracket at negative 2, that means negative 2 makes it into the intersection. If you put a parenthesis at negative 2, it means that negative 2 is excluded, is not included in the intersection. The only way negative 2 is included in the intersection is if negative 2 is in both sets. Is it? Well, negative 2 is clearly in the green set. Is negative 2 in the yellow set? No, because there's a parenthesis. A parenthesis at negative 2, because of that strict inequality, means negative 2 is not included in the yellow set. So then if negative 2 is only in one of the sets, that means it does not make it into the intersection, which means there has to be a parenthesis there, not a bracket. All right, we have the final graph of our solution set. Now let's write our solution set in interval notation. Interval notation says left to right. So it goes to negative infinity all the way to -2 parenthesis. So then any number that is less than -2, any number that is less than -2 will satisfy both of these inequalities here. Any number that is less than -2 will satisfy this inequality and also this inequality. All right, everybody, we have another compound inequality joined together by the word and, which means intersection. This will be our last example for intersection, and then we'll go to union. Let's solve each of these inequalities separately. It would be great if you paused the video and you tried these on your own, okay? All right, I wonder how you did. I got x is less than 1.5. Once you simplify 9/6, it's 1.5 or 3/2, right? And greater than 3. Now, I want you to realize that your answer is no solution. Let's see a picture, and maybe this might help us understand why that is the answer. 1, 2, 3. All right, everybody, watch this. Here's a picture to illustrate what's going on. All of the numbers that are strictly less than 1.5, strictly less than 1.5, look something like this. All of the numbers that are greater than 3 look like this. Strictly greater than 3, by the way. Can you look at this picture and tell me which numbers are in this like turquoise colored set and they're also in this yellow set? Right. There are no numbers that belong to both sets. They have nothing in common. What does that mean? It means that the intersection is empty. There are no numbers that are in both sets. So your final answer is no solution. Now, the way you would show no solution in a final graph, this up here, everybody, is not your final graph. That was just me brainstorming. So let me take that off the screen. So the way you would show no solution on a graph, it's kind of funny, but it would be like this. Okay, let's say this is your graph, and you want to show no solution, maybe something like this. Then your graph would look like this. That's it. It would be blank. Don't draw any arrows in any direction, nothing. Don't plot anything. Leave the number line blank. In order to write no solution in interval notation, that's a symbol for no solution. Check out this example. Before we go to union, check out this example. This has two inequalities written in one. So it's like 3x minus 1 is greater than, I'm reading right to left, okay, so it's a little awkward. 3x minus 1 is greater than 2, and 3x minus 1 is less than or equal to 8. This is called a double linear inequality. It's two inequalities in one statement. This is a type of intersection problem. The and is implied. So what I recommend for you to do is to solve this by isolating the variable right in the middle. So let's add 1 to everything. And then you would get 3 is less than 3x, which is less than or equal to 9. And then divide everybody, every term, by 3. And you get your final answer. 1 is strictly less than x, which is less than or equal to 3. Okay? This is great because when you have a double linear inequality like this, double because there's two inequality symbols, you can solve both inequality statements at one time as opposed to solving each one separately like we have been. The graph of this solution set would basically be all of the numbers that are between 1, and 3. So like if this is the number 1 and this is the number 3, all of the numbers, excuse me, between 1 and 3 would be the solution set. A parenthesis on 1, a bracket on 3, because this is strict while this is non-strict. This means 1 is not included, 3 is included. Interval notation would be a parenthesis at 1, a bracket at 3. All right, everybody, now let's transition to union kind of inequalities. See the word or is in the middle? Now this is a union type of problem. I'll remind you what that means at the end. All right, let's solve each one of these inequalities separately. For this one, what I'll do is I'll multiply both sides by 6 to get rid of the fraction. So this 6 and that 6 divide out, and I'm already left with my final statement, x is greater than or equal to 3, because half of 6 is 3. So there's that one. Let's go for the next one now. Just separate that. What do you want to do with this negative 2? Do you want to distribute it, or do you want to divide both sides by negative 2? I've seen most of my students want to distribute it. So that's fine. We can distribute it if you'd like. So this would be negative 2x minus 2 is strictly greater than 4. Adding 2 to both sides leaves us with negative 2x strictly greater than 6. Dividing both sides by negative 2. Remember, we're dividing by a negative, so we have to switch that inequality symbol, less than negative 3. All right, everybody. Let's go to show the graph of the solution set. Now, remember that we're talking union here. Union, okay? I'm going to make this negative 3, negative 2, negative 1, 0. 1, 2, 3. Okay, let's graph these. This one says any number greater than or equal to 3. Greater than or equal to 3. Greater than or equal to 3 looks like this, greater than or equal to 3. This one says strictly less than negative 3. Strictly, that's a parenthesis, strictly less than negative 3. That's a parenthesis right there. This is your final solution set. Remember the union of two sets. The union of two sets says that any number or any element that's in this set or in this set, make it into the union. You do not have to belong to both sets. You just have to be in one or the other. So any number that is strictly less than negative 3 makes it into the union. Any number that is greater than or equal to positive 3 makes it into the union. Interval notation from left to right. From left to right. This is an arrow approaching negative infinity. So negative infinity, comma, negative 3, put a parenthesis, union, bracket at 3, so I got to jump over here now, going all the way to the right, which is positive infinity. Don't forget that you always put parentheses, always, on infinity and negative infinity. All right, everybody, this is our last example for this section. Let's solve each one of these separately, each one of these inequalities separately. Remember that the word or implies union. All right, here we go. Negative 3x is less than or equal to 12. What I would invite you to do right now is pause this video, pause this lesson, and solve each one of these on your own. All right, I hope you did pretty well. I hope you did really well. X is greater than or equal to negative 4, or x is less than 2. Let's get the final solution set in the graph of the final solution set. All right, everybody, catch this, okay? Follow me carefully here, okay? I am going to plot this one first. Anything greater than or equal to negative 4. Follow me. Greater than or equal to negative 4. This will not be my final graph, okay? I'm just brainstorming at the moment. The next one says less than, anything less than 2. Anything less than, strictly less than 2. Look at this. All right, look at this. The union of these two sets says any number that is either, I'm just going to go ahead and call this blue and yellow. The union of the two sets says any number that's in the blue set or in the yellow set, make it into the union. So then what's your final answer? Here, let me ask you this. Does -4 make it into the union? Yes, because it's in the blue and it's in the yellow. Does 2 make it into the union? It's not in the yellow set because of this parenthesis, but it is in the blue set, so that's good enough. It makes it into the union. Does 0 make it into the union? Yes, because it's in both sets. Does 3 is over here, does it make it into the union? Although 3 is not in the yellow set, 3 is in the blue. That's good enough. Let me ask you this question. Does 1,000 make it into the union? 1,000 is way over here. Yes, it makes it into the union because it's in the blue set. Does -1,000 make it into the union? Way over there. Yes, because it's in the yellow set, so it's good enough. Basically, as long as you're in either one of the sets, you make it into the union. So really, you cannot find a number that's not included because these sets overlap each other, the yellow and the blue, and they're going in opposite directions. So they basically cover every single real number on the number line. In other words, the final solution set must be all real numbers. Everything is covered. How do you graph all real numbers? Like this. You draw an arrow going in both, making it really bold here so it can pop out, okay? You make an arrow going in both directions. That's all real numbers, and that's kind of ugly, but I think you get the idea. Interval notation would say -infinity to +infinity. That's your answer in interval notation. So before we end this lesson, I want to make sure that you're clear what this means. All real numbers means the following. Any real number you plug in will satisfy this inequality or it will satisfy this inequality. No matter what number you choose to plug in, it will satisfy one of these. It might satisfy both, but it will guarantee you to satisfy at least one of them. That's what all real numbers mean. All right, everybody. This is the end of this lesson. I'll catch you in the next lesson. I hope you took really good notes, and see you later.